The James Webb launched. There it is, right there. Look at that bad thing go.
The James Webb Space Telescope
All right.
will be on its way.
Here we go, folks. We're 30-some seconds in. We are getting ready. This telescope, incredibly larger than the Hubble telescope. A mirror made of gold.
Standing by for terminal count.
Cameras with untold capabilities.
Attention pour les deux comptes finales.
Here it comes.
10, 9, 8, 7, 6.
I believe they launched from Guyana.
4,
Of course, counting down in French here.
unité.
Here we go. And
engine start. And liftoff.
Décollage.
Decollage, liftoff from a tropical rainforest.
there we go!
James Webb begins a voyage back to the birth of the universe.
Look at that. Greetings, terrestrials, and greetings, Stephen. The date is January 6th, 2022. The Earth is in retrograde, and this is Strange Times Indeed with Cliff McCallister. I, of course, am your host, Cliff McCallister, the czar of the bizarre. Every week on this show, we take calls from our viewers to hear about the strange and unbelievable things they've witnessed in the world. Extraterrestrials, cryptids, interdimensional beings. If you can't name it, we want to hear about it, but not this week. This week, I mean, we're going to be talking about the cosmos. We're talking space. We're getting into the real nitty gritty of the future, of looking out beyond our own world and seeing what lies in distant galaxies. That's right, tonight we're talking about the James Webb Telescope. Oh, we'll get to that. Here's the thing, folks, that you got to know first before we get into it. Just a quick programming note. We're talking about the James Webb Telescope tonight, but we will need to address this real quick before we keep going. James Webb, just so you all know, we were asked, somebody brought this to my attention right before the show, said, hey, there's a kind of some homophobic history with this name. And I said, whoa, what the heck? And so I looked it up, and James Webb was a former NASA administrator from the 50s and 60s. He was largely complicit in the tracking and firing of LGBT employees during the 50s and 60s. So long and short of it, the stance here at Strange Times Indeed is he sucks. And during the summer, a series of scientists and astronomers, folks working within the program, signed a petition to change the name. And NASA looked into it and ultimately decided not to change. Not to change the name right before the launch. So tonight on the show, instead of referring to it as the James Webb Telescope, we, with the blessing of our wonderful guest, Dr. Kevin Hainline, will be referring to it as the John Waters Space Telescope, or the JW Space Telescope, or whatever have you, but there it is. That's what we'll be calling it. So without further ado, to talk to us about the John Waters Space Telescope, the next advancement, the big future of space exploration, astronomer, Dr. Kevin Hainline. Woo! Bring him on, Stephen. Stephen, we already have clearance to show his face, Stephen. You can, yes. I can't hear you. I can't hear you.
We're just going to triple checking that we got. Okay, here we go.
Dr. Hainline.
Hello.
Hello. Thank you so much for joining us here on Strange Times Indeed.
It's nice to talk with you, Cliff. Thank you. And I appreciate you dropping some knowledge about former NASA administrators, but I'll just be calling it JWST. There's an astronomer, Dr. Chandra, well, a cosmologist and a scientist and an astronomer, Dr. Chandra Prescott Weinstein, who refers to it as the Just Wonderful Space Telescope. But I think because we're kind of beaming out of Baltimore right now, John Waters Space Telescope is great. I mentioned that to someone recently, and they said they really don't know if they want super high resolution pictures from a John Waters Space Telescope. And I was like, I don't know, that sounds kind of fun.
But you never know what you're gonna find when you're aiming out there in space. So when I was talking to my pals about it, one of them suggested the John Waters Space Peeper, which seemed appropriate enough for him as well. But without further ado, Dr. Kevin Hainline, the JWST launched on December 25th. So how was your holiday?
Well, so I'm an anxious guy. So first off, I work at the University of Arizona. I'm a professor there, and I work on NIRcam, which is the primary camera on board JWST. The main camera is called NIRcam. It was designed and built by the people here at U of A. My boss, Dr. Marcia Ricci. You should look her up. She's incredible. One of the founders and mothers of infrared astronomy. She is the PI on the instrument, and I'm one of the scientists she hired. And so I've been working on this telescope for 6 years and thinking about it for longer than that. But for 6 years, I've been helping test the instrument and make sure it's worked. And so when I was hired, it was supposed to be launched in 2018, and it keeps being delayed, kept being delayed. And so there was a part of me that was like, I don't think it's ever going to launch. I don't know. Maybe this is just, it's a pipe dream. And even in the week leading up to the 25th, it was supposed to be launched on the 18th, then the 22nd, then the 24th, and the 25th. And so it just felt like this at finish line was getting pulled away. So when it actually was leading up to the launch, I couldn't sleep the night before. It was 5:20 a.m. in Arizona time. I couldn't sleep the night before. My wife went to sleep. My family went to sleep. Because my parents came for the launch and I guess for Christmas. And they all went to sleep, and I put on that new Matrix movie and then fell asleep right away. It was great. Thank you, new Matrix movie. And I woke up at 4 a.m. and I just was a ball of stress energy, just this freaked out ball, especially because I just kept assuming that they were just going to cancel the launch or delay the launch one more time. And what it actually was the 10, 9, 8. I was this is the time in which they would stop it. And I don't know how often a person gets a moment in their life where their entire career hinges on something that's live televised. But this is this thing was I was just sitting there thinking, if this blows up, I just am out of a job.
Yeah.
This thing in South America could explode and I would just not have a job. But as you saw, it launched successfully and it was beautiful and amazing. And I had a wonderful Christmas morning, the greatest gift of all time, getting a space telescope launched that was as smooth as it's been. And the last 2 weeks have been just so incredible to witness as the telescopes unfolded. So really, it's been a stressful holiday and now a kind of really exuberant holiday.
Yeah, well, so let's get into it. Tell us, what is the John Waters Space Telescope and what is it that we hope to achieve with it?
All right, so NASA and European Space Agency, Canadian Space Agency have worked together to build a space telescope that is the kind of next generation flagship observatory. It was first proposed after a very famous space telescope called the Hubble Space Telescope was launched in 1990. And so it is been 30 years in the planning. And the thing is that space telescopes are launched all the time. They're launched, and many of them are not launched with the fanfare of JWST, which is just the public was not nearly as super jazzed about the Spitzer Space Telescope, an infrared telescope that was launched, 20 years ago. But they're launched all the time. But what makes JWST so special is that it is the largest, most complicated thing NASA has ever done. It is an enormous telescope compared with Hubble. So the way I like to describe it, and I've got a little video where I describe it, is that Hubble's mirror, which kind of is the defining feature of a telescope, how powerful it is. The mirror on Hubble is about 8 feet across, which is a little bit taller than Shaquille O'Neal. I like using Shaq as a term of size. The samosa has just showed up for my wife. Sorry. Everyone at home, you're not getting a delicious samosa like I am. Maybe you are. I shouldn't judge.
If only you could smell this at home.
It smells great, which means I don't have COVID. I'm going to show you this here. I'm gonna make myself small and then show you this here. But this is JWST, and the mirror on this is much larger than Shaquille O'Neal. It's 3.5 Shaquille O'Neals. So Hubble's mirror would just be down here. But this is JWST. It's this enormous, enormous mirror on this telescope, and it has these 18 hexagonal mirror segments on it, and it's going to use this giant mirror to essentially look at things that Hubble couldn't see, because it's going to look in the infrared with incredible resolution, better than Hubble's, with amazing sensitivity and instruments and a wavelength range that Hubble couldn't see in the infrared. And so we're going to just uncover stuff that we've never been able to do before in astronomy. And I can tell you about that for the rest of the hour and answer all sorts of questions. But essentially, this is NASA and European Space Agency and the Canadian Space Agency, the next flagship mission to push astronomy into the next decade or so.
And you said you work at NIRcam. So what is specifically your role within this element of the James Webb or the John Waters?
So JWST, JWST has 4 cameras on board. Let me make myself large again. 4 cameras on board. And when we say cameras, we mean that when you have like a telescope like this, you've got a mirror and all that light gets focused into this thing right here, which is called the aft optic subsystem, which allows the light to go in to the other side of the telescope where we have this box. And inside of this box are 4 cameras, 4 fancy cameras in this box. And the cameras are called NIRcam, NIRspec, NIRIS, and MIRI with an M, MIRI. And the NIRcam, NIRspec, NIRIS, you could tell the NIR is near infrared and MIRI is mid infrared, which shows the wavelength range they cover. But as a scientist working on it, I've been involved a huge amount in testing NIRcam. We've done a lot of testing where we've taken the whole instrument and put it in a vacuum and at super cold temperatures and then turned it on and ran all the features of it. And I've also I've involved the testing when they integrated it with the mirror to bounce light off the mirror onto the instruments, a whole bunch of testing. And then I've been doing a bunch of rehearsals for the last year for what's about to happen, which is that I'm about to travel to Baltimore for a series of, because the mission control for JWST is right outside of Johns Hopkins. And so I'll be sitting in Baltimore like in a month as we turn the instrument on and then run it through its paces. And it's exciting, but also it's kind of like if you got a new digital camera for your birthday and you spent like the next 6 months going through every setting to make sure it did the thing it said in the manual. That's what we've got to do. Just make sure it works super well when it's out in space. So on top of that, all of that, which is like the thing that helps me, you know, like earn the right to the fact that when you build a space telescope instrument, you get a giant chunk of time, and my boss has apportioned to 400 hours of JWST time, 400 hours to point at a patch of sky and get incredibly deep distant observations of galaxies. And I work on that survey, which is called JADES. We use 400 hours of NIRcam time and 400 hours of NIRspec time from the NIRspec folks who built that instrument to make a survey of the universe that is like going to find the first baby galaxies in the universe. And that'll happen like in a year or a year and a half when the data starts rolling in.
Now, when you say 400 hours, is this like if you were taking a photograph, you're taking like a 400-hour exposure?
It's going to be a series of exposures. You could imagine just like opening up NIRcam, which is actually a rectangle, and just like peering deep. And that would be a thing. But NIRcam has a series of filters. So we've taken those 400 hours and split them among the filters we want to use. And there's lots of people who are doing these types of surveys where they open the shutter and look deep, but you want to do multiple filters so that you can compare what the images in the galaxy's light looks like at different wavelengths. But then also we're tiling a chunk of sky to make a bigger survey, because if you do these like really narrow beams, you're going to miss out on the diversity of the universe because you're going to be really focused in on like one tiny chunk. We're still looking at a small area compared with the whole sky, but it's a larger region. There's a very famous image called the Hubble Ultra Deep Field. And we're looking at a region that is about 16 times the size of it with our survey.
Wow.
Really big.
Yeah. And so do you get that big picture and then from there zoom in on other things? What is the process like once it begins?
Yeah. So what'll happen is we're probably going to get the data slowly because it's going to take a while, and we're going to build up what we call a mosaic, where we tile the images together and make a mosaic. Let me see. I didn't think about this, but this is a really good idea. Let me see. Brant. Can I find Brant's version 6 map? I want to show you. So when I first started working here, we started thinking we need to build like a fake universe so that we can build like that here's fake galaxies so that we can build fake images so we can test our methodology and our tools. And look at this. So if I bring this up and then bring this up and then drag this over here. Sorry, everyone, I shouldn't be narrating this. You can see this. And if I bring this up here, me put this right there. This right here is a fake. Actually, it'd be easier if I make myself small and then bring this up right there. This is a fake version of the thing we're going to see. And if I do this, it'll be in color, which is nice. Ooh. But what you see here is a mosaic. Ignore the fact that there's a patch here. This is all simulated. But this is a mosaic where the Hubble Ultra Deep Field is like some small chunk here. And if we zoom in, you can see every one of these is a galaxy. Every one of these is a galaxy. Galaxy, 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 galaxy. And this allows us to test our methodology, to look and see how well we can discern by looking at all these objects. You know, like, so if I put on this catalog, you can see that we put circles around them. We've detected them from the images, and I can click on these and say, here's how bright it is in each of the filters we're looking at, because we have different filters for every single, one of these mosaics that show you different, like the galaxies look differently in them all. This is just a color composite. And so our job with this survey is to look at all these and tell how bright they are and how many stars they're forming and which one's the farthest ones and what can we tell from looking at the galaxies as we march through time. But this is just a simulation of our survey right here, and it's been really, really, useful. You can even see some areas here where the mosaic's not as good. We're still working on it. It's a very complicated process.
Wow. Mm-hmm. Yeah, that's amazing. Here's a question. One thing that we talk about, of course, on this show all the time, the existence of extraterrestrial life. And I've heard one of the things they say about this telescope is it's powerful enough that we could potentially see life on other planets.
So that would be a hopeful thing. NASA's been trying to play down that because it's really a complicated thing finding alien life. A decade ago, it was thought that, if you could just find an atmosphere of an Earth-like planet and look in that atmosphere and see methane, you'd be like, alien cow farts, that's it.
Right.
And that's like what we call a biosignature, a tracer of life. But more and more in the last decade, people have been writing like, actually, there's ways that naturally methane can leak out of natural sources. So if you see it, it might not be the alien cows you think. So NASA's trying to play it down. But I will tell you what JWST can do. It can look at atmospheres of exoplanets. Imagine, so if I bring back up Space Engine here, boom. Imagine, so right now, this is a piece of software we're using here called Space Engine. And what you're looking at, if I shrink myself down, we can turn this off and bring Space Engine up here. You can actually see, we got the Milky Way galaxy stretching out across here. And then this little bright thing here, that's the Earth blocked by the sun. And I'm actually put myself right here in space where JWST is actually sitting compared with the Earth. But I also want you to notice that if I center on the Earth here and we zoom in using our little fancy zoom in tool, you can see that the sun's light is actually passing through the atmosphere of the Earth right here, which is kind of neat. And with JWST, we can actually do that for stars that are away from our sun, where when the star passes in front of, or the planet passes in front of the sun, the light from the star, not the sun, the star, the host star, the light from that star passes through the atmosphere, and therefore we can detect atmospheric signatures, water, methane. And what we'd like to do is see ones where maybe there's those types of biosignatures so that we can start studying them with other telescopes that are in space and on the ground to learn more about them. But that's one thing JWST will do. Another thing is JWST will allow us to block the light of stars inside of NIRcam and take direct images of planets. So there's lots of ways in which JWST can indirectly help us understand extraterrestrial life. It was not specifically designed as a planet hunting device like other telescopes in space are. There's this thing called TESS that you should look up, the Transiting Exoplanet Surveying Satellite, I think. And that's one that's like, we're just looking for these things all the time. But it turns out JWST is really good at faint things, and stars are pretty bright. And so planets are faint, but trying to block that bright starlight is difficult. And so there's lots of proposals for doing something like that better. But there are ways in which we'll make advancements with JWST towards the looking for extraterrestrial life. I'd love to find it. Oh yeah. So you're talking about the big strengths of JWST and looking in as far back. What are the astronomical implications of it all? Oh man. So when you've got a telescope this large in space, in the infrared, Hubble's infrared vision only went out a little bit into the infrared. So for those of you at home who are like, I don't really know what infrared is the part of the light that's outside of what we can see with our eyes. Our eyes see visible wavelengths, which is red, orange, yellow, green, blue, indigo. You can see it on my watch band, except you can't because I have a horrible green screen effect right now. But, you know, classic rainbow colors, right? But there's light that's shorter wavelengths than violet, and there's light at longer wavelengths than red. In fact, you interact with it all the time. You interact with radio light all the time. This is my cell phone. My cell phone is essentially a fancy radio flashlight. Radio waves hit it and radio waves go off, and that's longer wavelengths than the light we see with our eyes. And similarly, the reason you wear sunglasses or put on suntan lotion is because the sun gives off ultraviolet light, shorter wavelengths, and you want to reflect that off of you because it's not good for your skin. So you think about this, you just don't realize that it's just light like the light you see with our eyes. Hubble went into the light that was a little longer than what we can see with our eyes, but JWST is designed entirely to look only in the infrared. And the infrared allows us to see all kinds of stuff. For instance, behind me, you can see that I've zoomed in, but like there's a bunch of like clouds, it looks like, and that's just our galaxy's dust. Our galaxy and all galaxies are just filled with dust. And dust is great because dust particles are where molecules hang out and form in the universe. Pretty cool. The problem is that dust is like smoke, and smoke blocks our ability to see things in space. So if you wanted to look through big plumes of dust to like where baby stars are being formed, couldn't see it. The dust blocks the way. Hubble can't see through them. JWST though, in the infrared light just goes right through dust. There are firefighters who use infrared goggles to see through smoky buildings, to see people, things that are warm, to help people in buildings because they can't see with their eyes because it's too smoky. But with the infrared, you just see right through the dust to see the warm objects. And so if you wanted to look at a baby star in a cocoon of dust, infrared light allows you to see that. And these are a whole bunch of things that are doors that are opened with our ability to see the world in infrared vision. Things that previously Hubble could not do at a resolution that Hubble could not access. You know, like the galaxies that I'm talking about, the really, really far away ones. Like if I go back to this thing here, if I bring myself small, I'll go back this right here. These galaxies, like if I look up here, there's a bunch of numbers here. Hubble, this was the filter that Hubble could kind of do, F150, which means at 1.5 microns. So Hubble couldn't see the galaxies that only appear in this one, or only appear in this one, or only appear in this one, or this one, or this one. Like Hubble could not see a 4 micron image. And so if a galaxy only appears in these later filters, Hubble would not be able to see it. And why would that be the case? Because the internet or the universe is expanding. And so very far away galaxies are moving far away and their light is stretched in the infrared, meaning that it's only visible in the infrared. And so that's why JWST is like ideal for looking for faraway galaxies as well. So there's lots of implications upon implications. I'm gonna take a bite of samosa.
Go right ahead. I'm gonna say people in the chat are loving it. We got a question here going back to looking at exoplanets a little bit. Someone said, how do you go from images to signature detections of particular things like water? If that's not your...
What you do is you take a series of images along the transit in different filters. And JWST in NIRcam specifically has what's called a dichroic, meaning the light goes into NIRcam and then like a little usher sending the lights to its seats, the usher says, oh, you're a short wavelength light? You go this way, sir. Oh, you're long wavelength light? This way, ma'am. Short wavelength light, long wavelength light, and sends the light, splits it into 2 different wavelengths of light, meaning at the same time, 2 images can be taken, one at short wavelength and one at long wavelength of the same region of sky. And so you can do this to multiplex your science, and therefore you can take a series of images in different filters, and what you can do then is look for, so let me bring up a thing. JWST, you can take images to understand like how bright it is, or JWST NIRcam also has a thing that like disperses the light kind of like a prism, and that allows you to actually like look for the signatures. So like, gosh, this is a very complicated thing that I should not show people on a Twitch stream, but I'm doing it anyway because I think you guys are great. This is a transit depth showing like the light as a function of wavelength, and all these wiggles and the model differences. There's a model in here, and all the wiggles here and the model to it are wiggles from different molecules. And so it looks like the wiggles are just noise. This is just noisy, but that's not actually what's going on. The wiggles are things like methane. And so this is a no methane simulation, a 5 parts per million methane simulation. And you're seeing that they're trying to look and see, our models are doing pretty good, but we're not doing great at some wavelengths because there's extra molecules. And all these molecules are between signatures are 1 and 15 microns. JWST and NIRcam goes out to 5 microns, and then MIRI, which is the mid-infrared instrument, goes farther. So this is just a complicated way of saying that we can look at the light as a function of its component wavelengths to look for little wiggles, because molecules in atmospheres, when light hits them, they get springy and wiggle, and then they give off light at infrared wavelengths. They act like, imagine you had balls on springs and you kind of smack them and they kind of would vibrate around. That will produce light into space in the infrared, and we can detect that light as the light comes through the atmosphere, because the light is taken from the sun and sprang out.
Wow. Well, the smartest person I know commented and said, wait, you can split infrared light? Somewhere in my brain, you could only do that to visible light. I'd never considered it.
I mean, infrared light and visible light are like, it's just light. It's harder to do it for longer wavelengths light because you need to split it and you have to have larger things. But, the dichroic beam splitter is something that works at infrared as well. It gets really hard to do at very high energies. X-rays are really hard to capture. And at very low energies, because you have to have really large things to do the splitting. But infrared light, yes, you can definitely split infrared light into 2 different components.
All right. Well, Stephen, can you bring up that picture that I had sent you? So this is the very famous Hubble image, the pillar of creation. Mm-hmm. So what we are, and can you bring that off of Dr. Hainline's face a bit, Stephen? There you go. Thanks. So what you're telling us is this is just dust. Does it have any particular, is the pillars of creation the name because it's just kind of pretty? Or
so what you're seeing here, I'm going to reset Space Engine because it's acting up. What you're seeing here in this picture is a bunch of dust and gas, because this is a baby star forming region. It's a baby star forming region that's part of a much larger star forming region, which is, over time, gas and dust in the universe in a galaxy will coalesce gravitationally. Mm-hmm. And as it gets closer and closer and more stuff, it starts to collapse in on itself. And then you start getting regions where it's very dense, and that's where stars are formed inside of that. And so at the tips of those are, and throughout, are regions where there's denser material forming new stars. The reason it looks like that is because there's really bright stars just off the image that are so bright, they're blowing and blasting the less dense gas away. I don't often like to use this metaphor, but it's as if when you were born in your hospital, the act of birth was so destructive that it pushed parts of the hospital away, because these gas regions, they stop forming stars when enough stars are formed within them that they push the gas away, which is pretty amazing. And so I am very excited about this, because you can actually look at a Hubble infrared image from this to see what this looks like in the infrared and see the other stars. So let me do that for you all right now. Hubble infrared WFC3 pillars of creation. Because if you keep yours up, and then I show you the WFC3 version. No, that's not it. Is that the WFC3 version? Where's the WFC3 version? Maybe I'm.
While you look
this is
for
what
that,
I want. Yeah,
while you look for that, I'm going to highlight this comment from Mr. C. Dolson here. Says, when trillions of mommy dust motes fall in love with trillions of daddy motes, explosions. So here's the same image that we were just looking at. Ooh,
and then this is WFC3, which is Hubble's infrared eye, the little bit into the infrared. And I want you to notice how many more stars you see. These stars are all in this image, just dust is blocking them. Do you see how you can see through all of these? And because JWST looks at longer wavelengths, it'll even see through some of this thicker dust regions here. This should show you, this should be like your number one reason why you'd want to, why you'd be really excited about an infrared telescope, is because if you're a person, this is very pretty, but if you're a person who goes, okay, very pretty, but what's going on inside? This is what's going on inside. so many stars. Our galaxy has 100 billion stars. And so looking in the infrared is really vital if we want to understand all of these stars and their lives and what's going on. And many of them, these are baby stars. These are like, you not see any of this in here, and you see all of these little baby stars. And if you really want to go in deeper, this is the only way to do it, is in the infrared. And remember, with JWST, with this instrument, this WFC3, this instrument has nearly like horrible resolution compared with what NIRcam does. So you're going to find an image like this. It may be one of the first images they do. I don't know which one they're going to do first. An image like this, to contrast with this, where you'll be able to like zoom in and zoom in and zoom in and be like, have such great resolution.
Wow. I can't wait. Kevin, I'm gonna give you a chance to have your samosa and me a chance to drink some water. Stephen, can we go ahead and roll the previously clip that we opened with? For anyone who missed that, you can see us watch the launch on December 25th. And we will be right back with more Strange Times Indeed with Cliff McCallister in just a moment. Everyone, thanks for tuning in. We love it. Don't change that dial. Don't go to a different Twitch channel. Please, it'll only be a minute, and most of you probably weren't even here when we aired it the first time. The James Webb launch, there it is, right there. Look at that bad thing go.
The James Webb Space Telescope
All right.
will be on its way.
Here we go, folks. We're 30-some seconds in.
T-minus 30
We are getting
seconds
ready.
now.
This telescope, incredibly larger than the Hubble telescope. A mirror made of gold.
Standing by for terminal count.
Cameras with untold
À
capabilities.
12 de Léo, attention pour les décomptes finales.
Here it comes.
10, 9, 8, 7, 6,
I believe they launched from Guyana.
4,
Of course, counting down in French here.
unité,
Here we go.
And
And-
start. And
allumage
liftoff.
EAP, décollage.
Decollage, liftoff from a tropical rainforest.
There
to
we
enter
go!
James Webb begins a voyage back to the birth of the universe.
Look at that. Greetings, terrestrials. The date is January 6, 2022, and you're watching Strange Times Indeed with Cliff McCallister. You're joining us today. We're chatting with Dr. Kevin Hainline, who is working on the John Waters Space Telescope, or the JWST, and we're going to bring him right back on. Kevin, you were just chatting with one of our viewers. They were asking, what's the importance of baby stars versus developed ones?
Mm-hmm. So the thing about stars is that every part of a star's life is pretty important. And there are people who study what's called main sequence stars, like our sun, which is like stars in their most of their lives where they're taking hydrogen and turning into helium in their cores. But eventually stars age and they become different types of stars. And that's important because we know that we're made out of materials. You can see the Milky Way here behind me has materials from many, many stars along a long time, you know, like at different chemical makeups, and that happens inside a star. So you might care about older stars. But then if you're a person who wants to understand how our planet formed, you want to understand how stars formed, because as stars formed with disks around them that help feed the baby stars, those baby stars will have disks that will form planets. And our sun formed the same time as our Earth formed, at the same exact time, 5 billion years ago. And so there are people who model this process of planet formation around stars. And if you really are a theorist who has models for how it works, you want a bunch of data on baby stars. And if they're shrouded by dust, it's pretty hard to find them. And so getting a good images and understanding these little star forming regions, pretty helpful if you're a person who really cares about how new generations of stars formed from old generations of stars.
All right. Thank you. Stephen, you had a question as well you brought up during the break. Would you like to ask?
I was thinking of this question when we were talking about Shaq earlier. The Shaq was described as the size of the mirror of the Hubble telescope. And then in theory, it's almost like 3 Shaqs tall, like this mirror, right?
3.5 Shaqs. JWST is about a 3.5 Shaq mirror.
3.5 Shaq mirror.
An adult giraffe.
All right. So, like standard HD definition is like 1,000 pixels tall. It's 1080 tall, right? 1920 by 1080.
Standard definition is 480, and then high definition is officially 1080, right?
No, no, 4K is what I think is 480 or like, right? It's like 4 times the height, but 4 times the height is also 4 times the width. So like the volume of pixels is like unquestionable. Like it's a very large number. Is there a number for how many times more the resolution is? I know it's just like,
how big is this file?
So much greater, right? But if we're 3.5 Shaqs tall, that's like what are we talking here? Like,
so how big are these JPEGs?
Yeah,
the resolution of Hubble versus JWST, it's hard to quantify in a way that's like accessible, because like it depends on the size of the pixels, and also it's harder to get resolution when you're at longer wavelengths because the light is longer, and therefore there's like an actual difficulty in getting better resolution at longer wavelengths. I can show I don't need to show a diagram. That's the worst. I shouldn't do that. But like it's better. That's maybe the best I can say. It's not, because it depends on the wavelength and stuff like that. So, the most important thing is that because the mirror is much larger, you're getting that much, like 6 times the amount of light every second as Hubble. So Hubble would take like, in 1 hour of JWST time, that's like 6 hours of Hubble time. So if you take, famous images that took hundreds of hours, now imagine taking that same hundreds of hours on JWST, and it would end up being 6 times the amount of light, 600 hours, 600s of hours worth of light, which is really great if you care about very faint things where you need to collect a lot of very faint photons.
Yeah, it's like a faster download and upload speed then. Sure. We're talking.
Although upload speed is a little tough because it is so far away, it's 1 million miles away, and it we're actually limited in some part by the hard drives and the ability to send data back through what's called the Deep Space Network, which is a series of telescopes located in America, in Greenwich, and in Australia that allow us to talk to the telescope at a given time. It's kind of fun when I'm monitoring all of the process of deployment. We could talk about that for last week. There have been moments where they've been like, oh, we're about to lose line of sight with Canberra in Australia, and then we're going to pick up the line of sight in this place near Barstow, California, which is another one, and then we move away, it's Goldstone, and then move away to Greenwich. Like, it's just funny, these 3 things that are talking to the telescope right now, and that limits us in how much data we can take. Is that we'd love to just take data after data after data, but like super engineering grade solid state hard drives, that can survive tens and tens of years on solar power in space, you can't make them with like terabytes and terabytes and terabytes, because it's very hard to make those.
Wild.
Cool. Thanks for the question, Stephen. So you were just talking too about the deployment process.
Yes.
This telescope is going, I believe, literally 1 million miles away from the Earth.
Yes.
How does it even stay in orbit out there?
Yeah, so that's a really good question. I also want to answer. There was a person who asked a question that I was going to answer, and then I had to log into Twitch to answer it on Twitch. But someone asked a really good question, which is, in the pillars of creation, are the stars inside or are they behind? And it's that they're all inside together, and like there's much like it's. Some stars are probably behind it, some stars are in front of it, but the majority that we're seeing in that are probably inside of the gas cloud itself and the dust cloud. And if you remove the dust, you're just seeing them and able to see them all better. It's very hard in space to tell distances to things unless you're very clever. So let's take a look back at the internet here. But actually, let's shrink myself down a bit and then
Can
look
I
at the
ask,
internet.
Kevin, the
Yes.
picture behind you, is that just dust?
What you're seeing here is the Milky Way. So this is just the Milky Way seen from the side here. So if I zoom out, you can see the Milky Way and just really get a good look at the fact that it is a lot of dust. All the brown you see
okay.
in a galaxy image is dust, right? And it's multiplied. You can see it a lot better when you're looking sideways because you've got a whole bunch of dust along your line of sight here. But yeah, when you look in the night sky, you see dust. And I want to highlight, speaking of Australians, the Aboriginal Australians, when they looked out at the night sky in the Southern Hemisphere, they're one of the only cultures that use some of the dust in the Milky Way to give a shape for a negative space object. Most cultures would always just like connect dots or say this looks like an object, but using negative space, that was a unique thing to the ancient Aboriginals who lived, the indigenous people of Australia. So shout out to them. That's a pretty cool thing. Anyway, this is just fancy dust out in the Milky Way. I'm using a piece of software called Space Engine to fly around. That is very finicky. Here is our web, Where is JWST tracker. And this is something that I've been using a lot, which shows a whole bunch of stuff. For instance, it shows how many days it's been since launch, how far away it is right now, 630,000 miles away right now, but it still has almost 300,000 miles to go. It's 70% of the way there in terms of distance, and it's going about 0.27 miles per second. And then this is the temperature on the hot side of it and the temperature on the cold side, but these are measured at different spots, so that's why they're different temperatures here. This also gives you a look at what's been going on with the telescope deployment. And so what you're seeing here is you're actually seeing that today, this morning, they opened up this little thing called the ADIR, which is the Aft Deployment Instrument Radiator, which is just a thing that opens up that allows when the instruments are running, they get warm. You know this because you use your cell phone, and your cell phone, as it runs, it gets warm in your hand if you use it a lot. And we need to vent some of that into space, some of that heat. And so we just open up a little radiator, which just allows us to vent that. And that opened up today. But there's been a bunch of other stuff that's happened. You can see them listed here. If I click on time, you can see that these are now days, that we still got about, 2 weeks before we get out to where it's going to go. But there's been lots of different deployments that have happened. And so if you scroll down, you can click on like explore all deployments and see all of the different things that it's had to do over the last couple of weeks. This is a great website. It's definitely a website that I've just been looking at a lot. The big thing that happened yesterday was that we locked the secondary mirror into place. That's what you're seeing here. Whoops. You're seeing this here, and that was a really amazing thing. But the most impressive thing that happened was that the sun shield, this big piece of Kapton, 5 layers of Kapton, very thin layers of Kapton, was deployed and tensioned so that it can keep the telescope very cool. It has to be very cool on one side because the sun is really hot on the other side, and it has to be cool because an infrared telescope, if it were warm, that light from the infrared of the telescope itself would leak into the cameras, and that's bad. You don't want that. But there's been lots of stuff. But the question you asked, and I should get back to that question. The question you ask is, what happens when it gets out to this thing that says L2? How does it work then? How does it stay there? What is L2? So what we're going to do is I'm going to bring up a YouTube video. We're going to watch this YouTube video together. Sorry, everyone, if you didn't want to watch a YouTube video with a scientist today, but that's what's going to happen. So if I bring up the internet again, you can see the video here. And this video is going to show you what L2 is. L2 is a spot in an orbit that is Lagrange point 2. It's in a spot where if you see the sun here and the Earth, it's a spot that's 1 million miles from the Earth, 4 times as far away from the Earth as the moon. And it is a spot where the pull of the sun and the Earth together and its desire to go off in a straight line balance. So it kind of wants to stay there, but it's not going to just sit there. It's actually going to orbit in this fancy circular orbit like this. So this is a pretty good video to show off. It's probably very small for you, and I apologize for that. But you can notice as we zoom in that it's in this fancy orbit where the bottom, the sun shield, is always pointing towards the sun and the Earth. So that means it will always stay hot on one side and allow it to be very cold on the other side. So that's the animation of JWST's orbit right there. And if to stay here, to stay in that spot, it actually has to use a little bit of fuel to do something called station keeping, which is where that's not perfectly stable, that orbit. It's a little bit unstable. And so it uses a little bit of fuel every once in a while to kind of keep it there. And when that fuel runs out, JWST floats off into space.
And when it floats off into space, then we just lose it, I suppose.
Yeah, here's a simulation. Are you ready for the simulation?
Sure.
Oh no! Sorry, that's a joke. That's my dumb joke. No, we lose it. It goes off into space, and we at that point we can communicate with it, but we can't control at that. It'll just float off. And so that is a thing where we're monitoring how much fuel is going to be left over after we park it. And so in the next couple of weeks, we're going to have a final understanding of exactly how long it's going to be. It was designed for 5 years with the hope that it would get to 10 years. However, they've done 2 burns already. They've used up a certain amount of fuel just to get it on its way. These were planned burns. And after the second burn, NASA came back and said, we did our math. I was on the meeting here. It was a very, very exciting meeting for me. We did the math, and we have enough fuel for, this is the official NASA quote, significantly more than 10 years of life for the telescope, which is really exciting.
Wow.
They'll probably revise that and explain what significantly more means. I know what the numbers say, and it's a really, really good news if you are a person who's excited about more than 10 years of life on this incredible instrument and telescope. 5 years would have been such a bummer because it's $10 billion, and scientists have been working on this for 30 years. And significantly more than 10 years is like a really exciting thing for us scientists who want to use the telescope.
That is so cool. A follow-up question about its placement out there, coming in. What exactly is it orbiting? What kind of gravitational pull is it? Earth?
Yeah.
Is it
So,
moon?
golly, let's get into it, folks. Let's really get into Lagrange points, I guess. Lagrange gravity. Let's just do that. I want to find the gravity map. So again, I apologize if this is something that you're like, please don't talk about this. This is so tedious, but you asked the question, so we're answering it. So this is the Wikipedia page for Lagrange points. And what you're seeing here is you're seeing a map where these lines, these circles, it's like a topographical map of gravity forces. And so, the sun is pulling gravity pretty hard. The gravity near the sun's pretty high. So that's what you're seeing here. So you can imagine that this is like a ball sitting on this point would want to fall downward this way, right? But a ball sitting here would either fall this way or this way. A ball sitting at L5 would fall down in every direction. That's unstable. You wouldn't want that. You wouldn't want a ball sitting at L5 because it would sit there. However, L2, this Lagrange point 2, it's actually stable in 2 ways. If you put a ball here, it's going to fall down in this direction towards the same point. Like imagine like a saddle point, right? Where in 2 directions, the ball would fall down there, but the ball actually, if it goes straight in either direction here, would be unstable. The thing is that this saddle point's exaggerated for this figure, but in actuality, it's pretty smooth. And what that means is you can put an object in orbit around this point here, and it will be, like imagine a ball kind of going around on the saddle point where you only have to kind of give it a little bit of push in certain spots, but it kind of will oscillate back and forth up and down these hills as it goes around there with just a little bit of extra force to kind of keep it from drifting a little too close to the Earth or a little too far away. Does that make sense?
I think so.
Yes.
It's complicated.
Yeah.
I get it.
Good. There you go. That's all I need to do.
Just especially if you just imagine that there's a ball out there. Now this ball's invisible. It's just the center of gravity. It's not. There's not a planet or a moon or anything out there.
Around in the air of some sort.
We're orbiting something like a point where everything is like falls towards it, and that's what the satellite, the telescope rather, is orbiting.
Yeah. It's just. This green point here is the actual spot, but if you had a ball up on this hill, you would roll down this and then roll back and forth, right? If it rolled a little bit too far this way, it would go. But if it's very flat, like a very flat surface, it'll go. And there's whole YouTube videos with really smart physicists that are talking about this a little bit. But I just like to think about this. if there's anything that's just word to describe me, smart is not the word to describe me. I'm just passionate. That's all you need to be, by the way. Then this thing will just kind of orbit around in this circle like that. And we do that because that allows us to not have to worry about the moon. Like if it was directly in a line of sight, then sometimes the moon would block the way, and that's not great. And having a big circle like this allows us also, and JWST will have a little bit of sway in a couple directions so that we can look at all sorts of stuff, even though there are certain parts of the sky we'll only be able to look at some times of the year and vice versa, because the sun will be in the way.
Wow. Well, I've got to, now that we're talking about things moving in circles, we got to have a physical challenge. Kevin, both you and Steven know how to juggle.
Oh, gosh.
Let's get a quick juggle off.
Oh, shoot. All right. I never was a professional juggler of any sort. So I'm going to and I'm also sitting in front of a green screen
juggle off
here. So we'll see. And it's been a little while. So I guess we're ready for juggle off.
If Steven can only find his green screen juggling things, you might win.
I have some green screen juggling things. Shout out to Grandmaster Ong, who's in the chat. He's a juggler on Twitch, and he does a lot of things that are like it's contact juggling with clubs, where he's just touching it the whole time, and they're orbiting around. I'm trying to tie this into science. Orbiting. That. Well, I mean, it is science. It is science, physics, right? But yeah, here we go. Let's do some juggling now.
The gathering of the juggle-offs. Oh gosh, this is so hard in front of my webcam, especially because I don't have...
All right, here's a question from the chat while y'all are juggling. This is a genuine question, but there are no stupid questions.
There are no stupid questions.
Is there any chance of space debris damaging the telescope? And
so it's a little far out to be damaged by a lot of earthbound space debris, but micrometeorites and little tiny things like that, they're actually probably going to damage it over its lifetime. And they're going to be that sun shield will probably have a bunch of little holes in it from micrometeorites. And there's nothing you can do to block it. They're going too fast. You wouldn't want to put lead. It would also be really heavy. So the sun shield's actually built in a really amazing way, such that it actually, if there's little tiny tears, they won't spread across the sun shield. It has these little things called rip stops. Whoops. Well, that's it. And the rip stops. Right. Oh, look at you! Look at him dropping. If I could stand up and not sit in front of this thing, I could do more cool stuff. But
we appreciate the stuff you did. It's fantastic to watch.
Yeah. So anyway, it's also been a while since I've juggled, and I'm wearing a sweater and sitting down. Anyway, you beat me. I lost the juggle.
Hey, you did it great. It's not a competition. It's just to have fun. Give it up do a round of applause. I don't know if the applause is working or not working. I feel so bad if you've spent your channel points on applause. Did the hands come up?
I didn't see it, but...
So,
I'm sorry, everybody. I'll try and redeem
the sun shield, and you see these little things that are across it. These are rip stops, meaning that if there's a rip or a micrometeorite that starts to tear, it will impact this and kind of pull this instead of damaging the rest of the sun shield. And so there is definitely a thing where the sun shield could, could get damaged over time, but it's been designed to work even with a bunch of little tiny holes punched in it. And the way that it works is that it's tensioned with these layers here, and you can see the layers act to take the heat and dissipate them out through such that it can stay very, very cold. There's a difference of hundreds of degrees between the two sides.
All right, we got a question from the chat. Why did we launch it from French Guiana?
So it's launched in French Guiana. You always want to launch space telescopes near the equator because that gives it a little more oomph. The equator helps it throw into space. Pretty cool. Because if you launch it up in the North Pole, it would just be, it wouldn't have a lot of extra motion. That if it's launched at the equator, gives it a little throw. The thing is it was launched from French Guiana because a French company, first off, colonialism exists. We don't need to get into that. But the French people colonized French Guiana, and a French space company has put a rocket launch site down in French Guiana. This company is called Arianespace, and they've had a very good track record. And because this is a European and American and Canadian space telescope, not just an American space telescope, we've launched it using the Europeans offered. This is the space telescope company, the rocket company we wanted to go with, and they did an amazing job. Such an incredible job with the rocket launch. It was really great.
My grandfather is not able to watch live, but did want me to share this poem with you before.
Oh, cool. Let's hear some poetry.
This is just from Robert Frost. It's not one of my grandfather's poems, but he just thought it'd resonate with you, and I love my grandfather, so I thought I'd share it. He said this is Robert Frost's Star Splitter, a portion of it that reads, "The best thing we're put here's for us to see, the strongest thing that's given us to seize with, a telescope. Someone in every town seems to owes it to the town to keep one. In Littleton, it may as well be me." A little poem about a telescope. Let's see if there's anybody think. Okay, one last question from the chat. As a scientist, what would be the concrete evidence needed for you to conclusively argue that we have found extraterrestrial life?
That's a really, really complicated question. And it's hard because as a scientist, you tend to both have to balance your own desire and want for something to be the case with, I really need this to be shown beyond a shadow of a doubt. And the problem is that science is never about shadows of doubt. It's about slowly building up evidence over time such that you can kind of say, more likely. I think that we're going to find it, and it's going to be something where at first it's going to seem like the most like that there's no way, and like it's going to have to be months and months, if not years, of continued observation to show that the initial observations were true, to show that other people who aren't the initial scientists have also shown the same thing on different telescopes. And then maybe if you see it on multiple telescopes for multiple scientific groups, that stays over the same amount of time, that's like some biosignature, and we then show that there's no other way that could be produced, that's when I probably would think, oh man, we may have found the aliens.
Yeah, and
the one thing that I am skeptical of, and I won't talk too much about it, is I don't know if we found aliens yet, and I don't think they want to come and hang out with us yet, because I think that humans have really, we've done a poor job of being living creatures on this planet and protecting the planet. And if I was an alien buzzing through space and I saw us, I'd be like, I don't need to talk with those folks. They are too excited about digital watches and burning coal, and I don't know. So, I'm kind of a skeptical person, but this is the wrong show for me to be skeptical on, and I apologize.
Oh no, you're all right. I mean, one of the things that we talk about on the show, do we believe they've come here? Absolutely. Do we believe we're not really ready to get in touch with them? Yeah, that too.
Yeah. I just think that aliens are would be the greatest discovery in humankind. And also, I tend to think of it, and I'm a very big Star Trek fan, like a stupidly large Star Trek fan. And this idea that aliens are waiting for us to get warp drive or something that really shows that we've got our heads out of our butts. They're just waiting for that. I kind of think that makes a lot of sense.
Yeah, I think what we really need is a peace in space agreement.
We just need a peace in anyone. We just need to, again, pull our heads out of our butts because we're really, really good at being short-sighted.
Well, Dr. Hainline, one last question for you, as we talked in the beginning about the name of the telescope. Mm-hmm. If you could rename it to something else, what would you recommend?
So I have always liked the astronomer Henrietta Swan Leavitt, who was one of the Harvard computers, a woman who was hired at the turn of the century to do mathematics at Harvard. And as part of the science she was doing, she was actually doing astronomy science. She was doing it essentially for all the men who were doing all the science, and she was just some woman who was hired. She actually just made a very interesting discovery about stars that change in brightness in a periodic way. And that science was what allowed Hubble to discover that the universe was expanding. And I thought, man, the Swan Leavitt Space Telescope sounds pretty good. There's other astronomers like Lucian Walkowicz, who's at the Adler Planetarium in Chicago, who's proposed the Harriet Tubman Space Telescope, because Harriet Tubman is thought to have used constellations like the Big Dipper to help guide escaped slaves as they escaped to the north. So there's lots of different people we can name it after. We've named a lot of space telescopes after white men. I think we've named one after a person of color, and it was the Chandra Space Telescope, named after Subrahmanyan Chandrasekhar. There's a Vera Rubin Observatory and a Nancy Grace Roman telescope that's going to be coming online pretty soon, and you should look up Vera Rubin and Nancy Grace Roman. I think both of them had Lego figures with them, which is a pretty cool honor, if I have to say. But I've always liked Henrietta Swan Leavitt, or Annie Jump Cannon Space Telescope. What a cool name. So that's my thoughts on that. But John Waters, why not,
They don't have to change the initials, at least.
Exactly.
And he's always peering in the windows. the windows of space. And I said too in the email, we might see water on planets, and planets might contain things named John. Very common name on this one.
Real quick, if you have something to hydrate with, go ahead and take a sip of water. You've been doing a great job both of you talking, because that was redeemed, and hats off to you was redeemed. So really, hats off to you, Kevin. Thank you so much for coming on. If you happen to have a hat that you can put on, please go ahead.
Yeah, 1 second.
Thank you very much. You know, it's great to end the show with, you know, a tip of the hat to our wonderful guest.
I mentioned that I'm a big Star Trek fan, so if any Star Trek fans in the room, they may recognize that this is the hat of the DS9 Niners baseball team.
Whoa.
That I happen to have because I'm a big dork. So hats off. Hats off. I have to wear a hat? Is that what the channel point?
Yes, it is. It actually is. Thank you so much. Yes. All right.
I'm gonna put up, by the way, a couple things here just because we're almost finishing up.
Yeah.
But
Please
you
put
should
up those resources.
Yeah, if you want to follow me, this is the Twitter and Instagram. But also, like if I do this, and can I do this live? That would be crazy. I have a Twitch account where I mostly just stream video games nonsense. But if you like video game nonsense, I have that. That's a possibility. I have been posting in the chat here, and every once in a while I do stuff, and it's mostly just variety. But also last year I embarked on I want to be a speedrunner, and so I speedran a couple games in the WarioWare series, and I'm the 4th best speedrunner for WarioWare Twisted ever, and it makes me feel very proud of myself that I got there. But you can follow this. I've been doing a lot of stuff about JWST on both of these, showing off these things, and you can ask me questions on all of these, and I'd love to talk with you all there if you have more questions about space. I love space. It's cool. It's the place.
Absolutely. Dr. Hainline, thank you so much for joining us today. I sincerely hope as we start to get images in from the telescope, you'll come join us again and tell us what
I'll come back anytime. This was fun. And we'll show off images, and I'll show you more Jade stuff, and we'll talk about the farthest galaxies and all sorts of stuff. So, you know, this was really, really wonderful.
Yes, thank you so much. And for those of you at home, if you've been enjoying this, make sure you follow Dr. Hainline. You got his Twitter there, his Instagram, his Twitch. If you're enjoying our show, you can follow us on Instagram at Strange Times Indeed, and be sure to follow this Twitch channel, twitch.tv/MetCountyNight. If you like what we're doing, you can support this show specifically at patreon.com/StrangeTimesIndeed. Well, there you go. That's all the plugs, folks. Thank you so much for tuning in. Thank you so much for commenting some incredible questions in the chat, and just so much thank you to Stephen and to Dr. Hainline tonight. What an incredibly fun and informative show. I hope to see you in the future, those of you viewing, and Dr. Hainline. Until next week, we're here with Strange Times Indeed with Cliff McCallister every Thursday at 9 o'clock. So until then, stay strange, terrestrials.